Uh, Today's speaker is Seema Satin. She is from ISAR Pune. She is going to join here as a DST woman scientist very soon. And she is mainly working on the Einstein-Langevin equation. It is a stochastic effect taken into Einstein's equation. Okay, Seema.
So thank you for the invitation. And so today I'm going to speak on Perturbed Einstein's equations with a stochastic source and its applications to relativistic stars. So the new Perturbed Einstein's equation are known for quite a long time, and the whole branch of astereosismology is based on Perturbed Einstein's equations, which are sort of deterministic perturbations. The new part which I'm going to talk about is the stochastic source. So a stochastic source given to which induce Einstein's perturbations. So the perturbations which I will talk about are also the induced perturbations which are stochastic in nature, which are different from what are considered for the mainstream astereosismology till now. So, and it is due to the stochastic source that these perturbed Einstein's equations also gain a stochastic nature. So fundamentally, from the first principles, it is a new construction for the Einstein's equations and general relativity. Though this new modification changes to the Einstein equation is very much validates the Einstein's equations, and it is not a deviation from the general theory of relativity. So GR is very much valid for that. So as we go ahead, we will see a lot of results, lot of equations, mathematical results, which are important to have a vague idea about the physical aspects of the same. So beginning with fluctuations, because that is the new part which I'm putting in. The role of fluctuations in natural sciences has been recognized recently with a Nobel Prize in 2021. So basically the fluctuations are a way of studying mesoscopic range physics for any physical system. Okay, so we have macroscopic physics, microscopic, macroscopic physics. The in-between range, that is mesoscopic physics, which has a very different nature than the micro and the macro, is a very deep area in all branches of physics. So this role was recently, as everyone knows, this Nobel Prize has been. So it is very much a hot topic nowadays, and still a lot of scope remains to progress further on these. From the mathematical side as well as the experimental side in physics. Okay, this is becoming again a very active area. Mainly in the literature of fluctuations, people consider thermal and quantum fluctuations. The thermodynamics, etc., is developed very well in the whole branch of science, as well as quantum fluctuations are considered in physics. I will mention later why the fluctuations which I am considering in general relativity can be different from these two. And there are lots of electrical circuits, lots of other mechanical systems where one can see fluctuations playing important role. So fluctuations in physics and astronomy is also not very old, and this is non-relativistic. This is Newtonian, based on Newtonian physics, where a very famous paper by S. Chandrasekharan Review of Modern Physics, article 1943 is what I would recommend everyone to look at, where stellar physics, fluctuations, Langevin equation in stellar physics has been introduced very well. Now, this branch, fluctuations in strong gravity regions and relativistic stars, is very much unexplored yet. Though there has been quite a lot of development regarding semi-classical case, but for the classical gravity regions, strong gravity regions, this is yet very much unexplored and also a desirable development at the moment. So I'll give a brief introduction of what is a Langevin equation in physics. So it started with the Brownian motion, particle performing a Brownian motion in a thermodynamical equilibrium bar. Okay? So the equation, this basically is known as the Langevin equation, where this gamma t is the stochastic term, which is a driving force. The small gamma is the friction coefficient, v is the velocity. So any equation of motion which has as its source a stochastic source can be termed as a Langevin equation where the stochastic noise is basically a noise. Noise has this property. The first moment vanishes, and the second is delta correlated is the ordinary Brownian motion. And there can be other. What's happening? This is not.
It's not working. Yeah, so you have to press this one.
Sorry.
This one you have to press to get the next line.
Oh no, I'm not. I'm just trying to get the pointer.
Okay, so the pointer is this one.
No, that's what I was doing.
But it's not working.
No. Okay. Or you have a rod, I can just, you can give that. That is fine. Yeah. This is good. And I can just, to change the slides, I can use this. Yeah. So this delta correlated noise is the most, it's called white noise, Gaussian white noise, understand? And this with a stationary process can be addressed by this T minus T prime dependence of the noise. Okay. Now another important factor, this gamma T has a meaning only, it has a, when you take the stochastic averages around it. It cannot be treated like a deterministic quantity because this is the one random driving force, which then also makes V here a random variable. Okay. So these are few important points to remember because the perturbations which I am going to talk about are very well known in terms of deterministic quantities for some oscillatory kind of behavior, which I'll come later. So there's a difference between deterministic perturbations and stochastic perturbations, which is important to keep in mind while going through this. So fluctuations in astronomy and astrophysics have been studied to within stellar dynamics without the GR effect. In density and scalar field perturbations in cosmology are dealt with. The perturbations here, some of the cases there have been stochastic perturbations, stochastic averages taken, but that is in a very heuristic way. It doesn't come from any of the kind of things which I am going to introduce at the basic GR level. Semiclassical stochastic gravity was the first theory in which a Langevin-Einstein equation was proposed, but it is for the semiclassical Einstein equation. So you see the stress tensor. So this is the Einstein-Langevin equation. If you ignore this part, this is just the semiclassical Einstein's equation, where these two terms alpha and beta, they come from the fourth order expansion. Here we will say this is G is the background metric and H is a perturbation to the matrix. Okay, this is the Einstein tensor. Then you have the cosmological constant. And this term comes from renormalization of this. And there are other issues open whether this alpha and beta are zero or non-zero or they're small. But let's not go into that. There is this term on the gravity sector side. And this is the stress energy tensor, which has to be regularized for the where there are quantum fields and all. So semiclassical Einstein-Langevin equation theory has been developed by Bailov, Hu, and Verdagova. You can see the Living Review article. And so it's a very different. So this was the first thought given to introducing a Langevin noise into the Einstein's equation. The reason why it was simple to have this idea was that the stress energy tensor, which is composed of quantum fields, then actually the quantum fluctuations are always present. So adding a stochastic term, now this little term is the new part, which gives the Einstein-Langevin form. Okay, and this comes from the stress energy, the quantum stress energy tensor. So Bailov and they have defined this particular thing. Now this plays a central role in the whole theory. Yeah, this plays a central role in semiclassical Einstein equation, defined as the fluctuations in the energy stress tensor, the quantum energy stress tensor, such that this is zero. It satisfies the Langevin noise condition, that the first moment is zero. The second moment is a noise kernel. It is a bitensor given at two space tables, x and x prime, and consists of the stochastic average of the noise. So this basically defines the noise kernel. Now another important point to know here is that usually in the theory of Brownian motion and in ordinary physics, the noise is put in by hand, assuming some physical conditions like in Brownian motion, you take the delta correlated noise, white noise, or for some reasons you can model a colored noise. Here you would see it is the matter field for the Einstein-Langevin equation, the matter field as well as the space-time geometry. These two decide what this noise kernel, how it would be related. What this is. You cannot just put in hand a delta correlated or some assumption. That this is one place where you actually calculate the noise which hangs from the basic principles. And if you just put in these quantities here and expand them, I'll show you how. I'm just not trying to threaten you with the length of the equations, but show you how elaborate it has been, these developments. So you see this is all stress tensors, and when you have scalar field, the stress tensor for a scalar field is given in this form. This is the noise kernel with 4 parts, which looks like this. Huge expressions. And what are these G are Whiteman functions, 2-point correlations for the scalar field. So this is what has been obtained in the theory. The noise, the form of noise, has been obtained in the theory of semiclassical stochastic gravity. Now, having worked in, so I will just talk on semiclassical stochastic gravity here, because my aim is not to give a talk on semiclassical stochastic gravity, but the ideas that emerge out of after working on these. The question was, for the semiclassical case, you could do, can you do it for the classical case, and where would the fluctuations of the stress tensor be valid or of use or of application? So as you know, I'm giving a talk on relativistic stars and asteroseismology. Perturbations, definitely we can think of having some application there, which I've been trying to explore. So let me give a brief description of the Perturbed Einstein equation. So this is a simple form of Perturbed Einstein equation which I use in asteroseismology. They do the mode analysis. Here, see, there are 2 parts. One part is the matter sector. The other part is the geometry. So for the geometry, we have HAB as a perturbation, and usually in this this kind of work, the Lagrangian displacement vector, which is a shift in the trajectory of the fluid, is denoted by this. So these two form the fundamental variables in the Perturbed Einstein equation. Okay, and these, as I said, in the conventional way, these are deterministic. What I am going to show you, you will see that because of the noise, these turn into stochastic quantities as well. So, as I have said, but up till now, these are whatever I am showing you. These are well-known deterministic quantities, and their form and the way they grow or decay is of importance, even to gravitational wave detection and all. So these are very important. Okay. So the more I understand the frequency spectrum, there is information. And why do we do these studies? We do these studies because the characteristic frequency spectrum gives the information of structure, the interior structure of the gravitating body which we are studying. That is the importance of studying these perturbations. Okay. Then another part is, as I said, that one is interested in trying to know. The main aim is to know the interiors of the. One of the main aims is to know the interiors of the dense matter, which is still open in investigations. We do not yet perfectly know very well how does the matter and the dense matter stars behave. So I'm now slowly going towards the relative stars with this GR equation. The equation of state for dense matter and the relativistic stars that the relativistic stars are composed of is an open and active area. Usually, these relativistic stars are modeled by fluid description. So, a hydrodynamic approximation for the matter can say if you take neutron stars or more exotic stars made up of more exotic matter, okay, particles. So, the hydrodynamic approximation at the macroscopic scale for the matter content as a fluid and its linear perturbations are considered in the main framework of asteroseismology. So basically, the first model is the perfect fluid model for the cold stars. Okay. Then there are imperfect fluids with which these bodies are modeled. So we will be talking about perturbations of these models. Yeah? So let me give you some qualitative description of what I'm going to show you later. Before I show you the equations, you should know what I'm talking about. So a source of perturbations for relativistic stars can be introduced in the perturbed Einstein equation. See, when I showed you the perturbed Einstein equation, it's just that delta GAB and delta GAB. Now one can ask, what is the agency which perturbs it? Usually in astroseismology, it is considered that some external source has perturbed the whole system and one is not interested in the body which is perturbing it, considering it to be external. Now, suppose if there is something which is inside the body which can perturb, which can contribute to perturb any kind of perturbation, one can always include them in Einstein's equation as a source. Which so here I will you can have any kind of source, but what I am interested in is stochastic sources, okay, and the Einstein-Langevin equation. So specifically stochastic source which can arise at sub-hydromesoscopic scales. Now, I am defining these new scales for the relativistic stuff, sub-hydromesoscopic scales, which lie below the hydrodynamic approximation, where you consider fluids at macro scales, but it is above the microscopic scale. Okay, and it is at that length scale you would be able to see these effects, which I am going to show you. Okay. So, what does it give you? Why do we do these things? We do these things to probe the nature of the matter at those scales, which is yet unexplored. So that's the main interest, the physics part of it. Okay. And this idea is not something very new, because this is what we generally do in any kind of physics where we consider Langevin equation and stochastic processes. So these things have not yet been developed for the relativistic stars yet. So these are the first developments here, starting from the very first principle and the framework, and going ahead step by step. Such a framework would allow us to probe the structural properties and matter characteristics at mesoscales for the dense matter fluids, okay, as I have said. And for this, basically, now here we are dealing with the space-time structure. So we have to generalize the fluctuations, I call it just concept of generalized fluctuation, where the randomness is not only with respect to the time, but also with respect to spatial variables. Ordinarily, when we talk about stochastic processes, random processes, we say some physical quantities randomly varying with respect to time and so on. Here, for a space-time structure, it will always be needed that you put the space and the time variables on the same footing. So, the concept of generalized fluctuations has been introduced, okay, which also allows you to address roughness of properties. What does it mean? Say if you take pressure is a so the pressure in a fluid. Generally, when you say it is stochastic, it will it will have Pt, it will, and this is time with time, so it will randomly vary. Okay. Now, what I'm saying, when you have a stochastic process, I'm saying this x, where x is a space-time variable, which is let me put okay, x mu, say. So t r theta phi. It is spherical symmetry. So it will vary randomly with all of these or one of these. Okay, it is space and time variables. Okay. So that is a generalized stochastic. The concept has been used in many places, but basically for the terminology, I have to be specific that this is the case. Otherwise, whenever you say stochasticity, your first impression is the quantity is varying is random only with respect to time. Here I am very particular that it has to be, it can be stochastic with respect to spatial variables also. Okay, or it may happen that the quantity is varying smoothly with respect to time, but a roughness in a physical quantity, that does not necessarily mean roughness in the structure of the star, the pressure or energy density or any other physical variable. That particular quantity is varying, not the structure. It's not. It doesn't have anything to do with the structure, the physical structure of the space-time variables. For example, whatever I'm telling you, these quantities. So I said GAB is the background matrix, which is deterministic still in this theory, while HAB, which is a perturbation, is what is stochastic here. And psi is the fluid wave. This is stochastic. But GAB particularly are the background quantities for the stress, the pressure or energy density or core velocity. These are deterministic. Okay, only their perturbations will be stochastic. The background, so the solutions which you get for the matrix is GAB deterministic plus HAB. This is how it would look like. Okay. Now, matter field fluctuations, the generalized ones, can form an internal source for the Perturbed Einstein equations. This I'll put it in the equation. So I'm just explaining to you. These fluctuations in terms of the matter field of the star can be due to thermal. Now, one can ask the question, but why, how do these fluctuations arise? They can be due to thermal effects, they can be due to quantum effects, quantum fluctuations, mechanical effects of the bulk properties. I would be more interested in the bulk properties rather than UA, which is a kinetic term here. Okay, it is a local kinetic term. Generally, P and epsilon are considered as bulk properties in the fluid description. Okay, there can be dynamical matter. There can be several effects due to which the matter content can have these fluctuations at mesoscopic scale. There's a difference if I say the fluctuations are at macroscopic scales and mesoscopic scales. Though in general, like people have argued that it is a neutron stars and dense matter stars are very smooth quantities. What smooth fluid quantities? They are talking at the macroscopic layer. Nobody has tried to explore what happens at the. There are astroparticle physics who study the quantum particles and particle physics kind of a thing. Those are the microscopic. Our scales are much above that, but below the macrohydroscopic scale. One has to explore the range of mesoscopic scales. With this theoretical formulation and getting the results also, we would get an insight of how to probe through the mesoscopic range. But for that, the theory has to be developed from the first principle. So this particular theory combines the basic principles of general relativity, statistical physics, and stochastic processes together. So at this point, the basic structure is being, just begun for the classical case, I mean, not the semiclassical case. So, and all this development has to be tailored for relativistic stars only. So I'll just skip this, and basically this kind of a progress will enhance the the framework for mesoscopic scale in dense matter, dynamical equilibrium and non-equilibrium statistical physics and transport properties can be addressed if you study these fluctuations and its implications on cold dense matter of hot massive stars. Okay, now here comes. So I'll show a crude model for induced perturbations in relativistic stars with a stochastic source. As you know that solving the Einstein's equations analytically, the very few models we can do that. So as a step by the first step progress to get an idea of how do our expressions look like, how do the results look like, how do the fluctuations affect the main quantities. To get some idea, I worked out some crude toy models. So this was the first model I had worked out. So now this is classical. Okay, I have shown you the semi-classical thing. Here phenomenologically I have put this noise here, which is same as which comes from the fluctuations of PAB. Okay, you see G plus H, this is perturbation. So GAB of G will balance PAB of G. The Einstein's equation is satisfied. You can take that out, throw that away, and you remain with this. Okay. Here basically this is done in a common coordinate that this psi will be vanishing. You will only have this perturbation. So this was the first model I had worked out, very crude one. The stress energy tensor for a perfect fluid looks like this, where epsilon is the energy density, P is the pressure of the fluid. These are the four velocities. Okay, and another property is that this should be covariantly conserved. This quantity now. So delta A, this has to be satisfied. Okay. And similar to the semi-classical case, I have defined the tau AB, the noise as this, and 2-point correlation. Here for the classical case, since stress tensor is classical stress tensor, we get covariance. If you just put that in and expand, you will get twice of covariance of these 2 points. And so this first exercise was done here in 18, and this is in GRG. The first models have been accepted. So this is the form of the noise that we get. For non-rotating spherically symmetric stars, this is the line element. I'm just showing you the noise kernel comes like this. What happened? Something I missed. No. Okay. So I'll just go through it. And so the noise kernel now you see is coming in terms of covariances of the energy density. Sorry, there I had put epsilon. This actually is rho. I just copy pasted it from somewhere. This is 2 points. So this is the set of components of the noise. that we get in a relativistic star, a cold relativistic star. So pressure and energy density only. I'll just flip this and I'll show you the solution. Basically, the matrix potentials we want. We want how are the matrix potentials perturbed. So this is the form. You see this noise sitting here. Now, as I said, to have meaningful expressions, we need to take averages. So when you take the averages of these stochastic averages of these two, it turns out to be zero. So delta nu comes out to be zero. These are other factors, S1, S2. Don't bother about that. And you will see that what we are interested in, so consistently this goes to zero for a Langevin noise. Okay, the 2-point correlation is this. And here you will see that it is a cumulative effect over the radial vector for the covariances. So it is a cumulative effect which perturbs the matrix here, the 2-point correlation of the matrix. You can always find the root mean square by taking C tending to C prime tending to C and just bring the points together. So you will get a square and you take the square root. That will give you the root mean square. So root mean square is always non-zero. It's going to be non-zero here while the average is zero. So if you are interested in a single point, you can take out the RMS value and work with it. And now why are 2-point covariances really interesting? They're interesting because they help you to study extended properties of whatever system you are interested in studying. So this is the star. This is the center. So you take 1 point here, 1 point nearby here. So when you study these correlations, it gives you some idea about the structure of the thing. Okay, and especially in the strong gravity region, the curvature is definitely very important. So these you will see that these matter field fluctuations, covariances here, give rise to these perturbations, 2-point perturbations. So once you have information about this, you can play with it. You can explore and see like how far they can be placed. There has to be lots of physics comes in. So this is building up the statistical physics. And for Gaussian systems, once you know the 2-point correlations, it is in principle possible to work out all the higher order correlations, because all the higher order correlations for a Gaussian system can be given in terms of 2-point correlation. The 2-point correlations are very important here for the Gaussian. You can also study non-Gaussian systems. That is not ruled out, but as a first exercise, because it has mathematically many simple properties. So it's easier to work with it, get some information. So as I said, the cumulative effect of covariances and pressure and energy density, because the individual effects will be very small. It has to accumulate and push it further to to have that, to show that perturbation effect. So the nature of density and pressure above the average or the deviation from the mean and its distribution is of utmost importance to the Langevin analysis of the system, as we have seen. Then the important note again is the scales at which such a behavior is expected, mainly the subhydro mesoscopic scales. These scales are expected to lie somewhere below the macro hydro scales that assume a smooth variation of bulk properties like the pressure and energy. Where do we put our probes is very important. If you put it at a higher scale, you will there's nothing, everything is smooth. There are no fluctuations. But if you make your window, smaller and go, so at some scale, it is expected that you would see such things. Because at microscopic scales, we know there is this quantum fluctuation, that which scale that dies off or it gets coarse grained and shows up in the bulk properties of the fluid is an interesting question to ask. Equations would eventually give rise to hint us towards probing through those scales. Quantitative if you want the answer. Okay. The vanishing of, and you will also see that the vanishing of covariances of pressure and energy density will result in vanishing of the correlations of matrix perturbations. Okay. That's good. Now, a more elaborate, that was a toy model, very crude, a more elaborate formulation of the Einstein-Langevin equation I was trying to do, and this starting from the basic principle of statistical physics. If you ask the question, how does this Einstein
Excuse me, I think we can't hear you now.
Star, which gives rise to these perturbations. So this has to be a function of background GA. So this is the complete form of Einstein-Langevin equation. You see, and I'm going to do is show you a more elaborate solution of this. This way, again taking a spherical symmetric model with radial perturbations. Here, the line element, the stress energy with cold matter. Now, I'm going to ask a question: where does this seeds of perturbations come from? Okay. So it can come from the dynamics itself. Suppose one of the models is like, suppose the massive star is collapsing, you can have a cold massive stars, equilibrium configuration, and it's just collapsing. You can put it in coordinates, and near equilibrium it can be expanded around
the first order perturbation. That is what I'm going to do. The small amplitude pressure fields as origin of non-thermal noise in dense matter due to the dynamical collapse near equilibrium configuration looks like this. Okay, and where delta SPG, this is random, and omega R are random. The randomness in amplitude and phase arise due to the uncertainty in exactly determining this and the frequency around the regulation. This is the form of noise. These are the components of noise that we have for this model. You just plug in all these things and you work out the perturbation, which this is the perturbation in one of the potentials. You will see you have to take stochastic averages. Here, this average on here is actually an average in omega RT, but I've written it like this. Okay, so one can evaluate later, but you will see that for the Langevin noise, this particularly goes to 0. So the first moment goes to 0, but these expressions are very important because you will see that there are these factors y1 and y2, which are basically related to which are like this as a related to dependence of speed of sound in the dense matter, which is a parameter of utmost importance in relativistic stars, on how waves travel, how mechanical waves travel, shocks travel, and many other things from the astrophysical point of view. You see this coming in. The appearance of the, you will also see that here I have put R1 to R2. Okay, and another factor coming from the response kernel is this. Okay, which is basically which tells you about the susceptibility kind of effect, quantity, which CH has to be characterized, but you will see this quantity sitting here. This comes in these equations, which was not present in the earlier equation, earlier solution. So it is this quantity which decides basically usage of C minus T prime. Okay, so it takes care of the causality, and the causality may also be related to the speed of sound. Here in these equations. So this shows the dependence of speed of sound in dense matter. The appearance of speed of sound points to the possibility of associating the issue of disturbances in pressure and energy. What are these fluctuations doing? They are traveling. The information is traveling from say inside the star to, for example, it is going from the R1 to R. Supposing we are measuring here, so this disturbance is traveling, So this should be a causal effect, okay? And the speed would decide many physical aspects of the same. So these are the very basic equations. They are not manipulated. That physically we want some effect to come, so we modify them, but they are coming from the basic GR equations, putting very simple things in the beginning, and then we decide what are these equations giving us, what physical effects that all can be encompassed with these equations. So we really see very easily that the speed of sound comes in, and the causal effect comes in because of this factor, response kernel. So what is the susceptibility of the geometry to get perturbed when the fluid is getting perturbed? It's a very interesting thing, which is for the first time given here in terms of GR equations. Such things have not been studied because the basic Perturbed Einstein equations do not contain this kind of. This is a very basic principle of statistical physics here. So as I said, this indicates the dependence of perturbation on susceptibility of space-time to get perturbed. One can explore other models of response, and this is valid only for if the disturbances and the noise is inside. Suppose if you take another, I probably did not mention. Sorry to forget a very important point here, that this particular case, this kernel, response kernel, I have taken if it is delta correlated. Then you see the vanishing, it becomes the simple ordinary perturbed Einstein equation, which is the case. I can always put a condition here. If this K is delta correlated, we get the ordinary perturbed Einstein equation, which hold when the perturbing agent is outside the gravitating body. If it is inside the gravitating body, then this cannot be delta correlated fully. Okay, so I have taken a particular model where this is not delta correlated fully in both space-time coordinates. Then all these goes to. Otherwise, there is this whole branch of activities to be well established. You go to there are no stochastic effects there. Okay, so if this is delta correlated, then this tau is 0. You never put anything here. Yeah.
Just trying to understand something. I don't know if this cannot. So usually what I see is that you have some team union. And then you make a perturbation to team union only. And then the Einstein equation you thought should show you what is the effect of perturbation on G union.
Yes.
Right?
Yes.
But here what you are doing is that you are giving a delta G union also. No.
So
this so when you started initially, so I was seeing that on G you also some H.
No, that's okay. Let me just clarify here on the board that what I am doing is G is G plus H is equal to 8 pi T G plus H, right? And people usually use this trajectory. So these are both perturbed quantities where G will will balance. Sorry, GAT. So I understand your question. So now what's happening is, let me write. So this will balance this TG by the Einstein equation, the standard Einstein equation. What we are left with is GA is equal to 8 pi T H, and I will also put that psi because the fluid trajectory. Okay, this is the standard perturbed Einstein equation. So what you're saying holds over here. Now when I add, so I want to add. So the question here, what is the source of perturbations in both these? So this is one-to-one correspondence, right? If this gets perturbed, this gets perturbed. If this gets perturbed, this also gets.
Yeah,
Right. Now I'm asking the question: what is the source of these perturbations? What is the agency which pushes either the trajectories or this both? So H and psi are at the same footing. They have nothing to do with this, and they are not a part of this stochastic agency. So it is the stochastic agency which is pushing and giving rise to these perturbing quantities. Okay, so I'm going to answer what is the source of these perturbations. Here, if you don't put this question, you don't talk about what is the source of these perturbations. You don't know. I mean, they're just perturbed. And often in astrophysics they do because this is some external energy came and perturbed the thing and it happened. So I'm specifically because I'm interested in exploring the insides of the relativistic stars. So I'm bothering about insides. Can there anything be inside some dynamical quantities or thermal quantities which can perturb the system? So that is what I'm dealing with here. So you see this delta, these results coming in terms of the noise. So this is part of the noise, very, very easy. So again, the same thing, it is a Langevin noise. So the first moment vanishes, this will vanish. And what we will get basically is the second moment. This is e raised to I omega t is this has to be a complex conjugate of this. So 2.4 correlation is the usual way that we take. So we will be interested in these expressions, You see this susceptibility kind of thing coming over here. Okay, so lots of information on this one can say. Now, certainly, if you are interested from observational point of view, you will not be able to measure these individual fluctuations or even their correlation. What you will be measuring will be these quantities, the fluid trajectories or these things, and you see that these are very tiny, you have to integrate over a whole lot of the whole range, then you get this effect which physically looks meaningful. So these, even though these are mesoscopic effects, this can, these are integrated cumulative effects, and they can also go, and these mesoscopic scales can also give rise to macroscopically measurable things, some little bit of perturbation in macroscopic things. Okay, so it is not that these are futile, just theoretical exercises. You definitely can, in some cases, not all cases, where there's a growth and all, you definitely would be able to see it somehow, it will be measurable. Okay, and about the Gaussian distribution I already mentioned. Okay, now this is one branch. So this finishes off one part of the talk in which this Einstein-Langevin equation I was dealing with. The next part of it is another branch, side branch coming out from these studies. It is about I had shown you the long expression of the noise kernel at the beginning of my talk, which was the part of semiclassical theory. Now, another branch comes out because we are working on the stochastic person noise for the relativistic stuff. We have this hydrodynamic limit of scalar fields.
Excuse me, may I ask you a question?
Scalar field, stress tensor for scalar field and a stress tensor for fluid has been very well known since ages. Fluid approximation of fields is an active topic, and using our noise kernels that we have talked about, I have shown a correspondence. So this is the general correspondence, is well known, which is this quantity is the 4 velocity, energy density, Q is the heat flux, P is the pressure. These are the anisotropic stresses for an imperfect fluid. Okay, and these quantities you see phi are the scalar field. If you see the stress tensor, you see the size here. This is the coupling constant here also. So I'm going to show a relation between the fluctuations of the stress tensor in the two cases, which is correspondence of scalar field fluctuations and fluid fluctuations in hydrodynamic approximation. So the fluctuations have not been worked out. So this is a part of the work which has noise kernel, which I showed you earlier. So these are again the Weissman functions, which are 2-point functions of the scalar field. They have, these correspondences with covariances of our quantities, fluid quantities. So this result has been published in Maxwell was the one in 1988. I think for the first time, also anybody had done it before this, I do not know. In 1988, he worked out the correspondence between the stress tensors, the two stress tensors. I don't know before 1988 anybody had done it. This has been widely used in cosmology. So the first paper has been, these are the different various kinds of perfect and imperfect fluids worked out and their comparison with the noise kernel, because we can even solve the semiclassical Einstein's equation in the decoherence limit for the case if we use our correspondence for the fluid correspondence. So lots of problems opening up with these basic exercises. Okay, so in the second direction also we have this thing coming up. The solutions for dynamically collapsing models in non-equilibrium case we will do next. This was basically equilibrium thing which I'm working as a first exercise. After this, more interest is towards non-equilibrium cases, though in equilibrium cases also we can have many things. For example, the gravitational wave people are now interested in mergers and binary systems and all. Those are further on, but not too far. There are 1 or 2 steps we might also reach there once we figure out what parameters exactly we want to study, like these fluctuations, how do they affect the collapse parameters, near-critical point if you see stability issues. So near-critical points when you see a fluctuation can trigger a non-equilibrium phase in the system also. So further on those things most likely are going to be done by numerical relativity people will be needed as far as I think, because the equations are very involved. But we still have to try some toy models as a first stage and then go on further. But this is the scope of further developments in this area that's coming up. The fluctuation dissipation relation from statistical physics point of view is a very important relation, and it will be very interesting to see how we can have a fluctuation dissipation relation for a quartet configuration of relativistic stars. So, sorry. Using different matter fields, like we can, some of the stars also have additional electromagnetic fields with them. One can see how the fluctuations of electromagnetic fields, are they of any use, what do they give us, and how do the expressions look like? People would be interested in that. Because a lot has been studied. And there's been, on the fluctuations, there can also be dragging effect in the strong gravity region, which can again, make them grow. How would that affect the system? So these are some interesting exercises to do and see. And consequences of generalized stochasticity and mesoscopic effect of the parameters, as I said, governing different collapse and different dynamical equilibrium states of the relativistic stars, accreting delts and binary systems may be interesting to study. So with this, I can definitely say that identifying new modes of oscillation, random oscillations for relativistic stars, which can, maybe one can call them stochastic modes, kind of thing. I don't know if that term already exists for something. So maybe stochastic modes one can call, where you study the RMS values of the modes, basically, if you are looking at the single point or point separate. I don't know how we would see, but those kind of lot of things can come up. And this I've already said. Connections with quantum fields using hydrodynamic generalized equation. The second branch, which I said, it leads towards the possibility of a kinetic theory in closed space-time. Okay, using this approach. Now, why this? Why is this interesting? Because particles, the particles do not have globally in closed space-time. You cannot globally define particles, the concept of particles. But you have fields and fluctuations of fields. If they are more fundamental, then we can probably build up a kinetic theory in closed space-time using this fluctuations approach rather than particle approach. Is some idea floating on my mind. And I will conclude this talk with these remarks. With the basic formalism presented here, that of Langevin approach for gravitational systems governed by the Einstein's equations, a new direction for perturbations in relativistic stars is open to detailed investigation. It needs development of rigorous force principles. So the basic toy models are not unimportant to work on here. Okay, because correctly one has to combine the basic areas, the statistical physics and GR, the equations. They should properly be framed properly. The mathematical formulation is very important to the correctness of what we would see later. Okay, so it needs rigorous development of rigorous force principles while combining the robust framework in GR and equilibrium and non-equivalent statistical physics. The dynamical, non-thermal as well as thermal statistical properties of the gravitating bodies can be proved through with these developments. And relativistic fluids, the last point as I said, at subhydro mesoscopic scales can be explored as part of this research team, where kinetic theory may be based on the generalized fluctuations rather than the particles. So these generalized fluctuations can replace some of the particles as the idea. Thank you. Yeah.
Please go ahead.
So we are taking on psychosymmetric star and perturbed radial. So if I assume that if the perturbation will deform the star and the star is not spherical, that is content is microdomain, then can we use the same formalism to calculate the normal?
Yes, very nice. The only thing is the solution of the equations is difficult. You may have to do it numerically depending on what form you are taking. So spherical symmetry is required because analytical results are simple to work out. If you deviate it, then many times, just like what you do in GR, so many times you have to numerically solve it. But definitely you can apply this formalism to any. In fact, that is the main interest. We don't want a very spherical. This result is not so interesting that way in the sense for observing things. You definitely can apply. This is the beginning. The next step would be what you are saying. Yes.
So, you're studying the mesospheric fluctuation, fluctuation at mesospheric scale.
Mesoscopic.
Mesoscopic scale for relativistic stuff.
Yes.
So, why can't we study for other systems?
Other things.
That's
So there is a whole lot of literature already present. Non-relativistic things, as I said in the beginning. Physics, all branches of physics contain a lot of things. It's very rich.
This is where your Brownian motion and all those things are. Einstein, in fact, started.
Yes, yes. It is the other way around. We are borrowing whatever they had, that was the idea from, and putting in here.
But one this thing, if there is a vacuum, still there is some geometric structure to the like there are black hole and other things. So there are some statistical interpretation of. So is there some way this can be brought into the stochastic terms
So,
in the vacuum?
So I would say that if you just it as a black hole, then you cannot. But if black holes are immersed in some kind of field, like electromagnetic fields or any other fields, then you can think of, because here the matter fields are important and their fluctuations. In principle, if you do not have matter fields and fluctuations, then this is not what you would be doing. But you can always have black holes emerge in some kind of a field, and you see the fluctuations of this. In fact, I have sort of worked out noise kernel for Riesman Oscapin Gaussian matrix. Emerge in thermal fields. Then you can apply this.
But point is, when you don't have any matter, let's say no matter, but still GR has a non-trivial solution. What happens to this case?
This case is not applicable if P nu is not. That is factorization. Something has to be there. You can obviously then you have a different formulation for GR for that black hole. You can of course have a different formulation, but this won't fit in there.
So that means to say that statistical thermodynamic interpretation for the black hole cannot come from.
No, I'm not saying that. I'm not saying that. I'm saying that thermodynamical and statistical interpretation come, but this particular Einstein-Langevin won't fit in there. That's all I'm saying. We will have to modify that accordingly. What the physical system is, you can of course have some source of fluctuation or something, but that will be a different formulation than this Einstein-Langevin equation. That's all I'm saying.
So, another case is electromagnetic.
Yeah.
Electromagnetic case is another, which is not really vacuum.
That we can of course say. If that we can take that for electromagnetic, and that's in fact I'm planning the next step over that also, because now I have taken for fluid. I can take electromagnetic field and look at their fluctuations. Or you can take both. You can take P mu that for the fluid plus the electromagnetic also. Combined, because stars are embedded with this fluid plus electromagnetic field. Say. And as I said, on the electromagnetic, the dragging effect would be very interesting to study this on the fluctuation. Yes. So all those things can be, definitely we can do with that. So for the P mu, we put in whatever, you can put in whatever matter fields you are interested in exploring. But you have to put together 2 or 3 types of P mu also, like for electromagnetic plus imperfect fluid, and see if one is, they have any interaction or they do not interact. Lots of possibilities to explore. Yes, more. But individually also you can see, so if you take a black hole, imagine an electromagnetic field, we can have this P mu fluctuations for that plus P mu for, we can see the output how the fluctuations behave there. That would probably definitely, that is definitely possible.
I have to please go ahead.
So Mike, I have 2 questions. Can you hear me? Okay. The first question is, you never bothered about the coordinate transformation in independent property, right? In general relativity, when you transform things, you have to worry about the gauge transformation, because what you are calling perturbation may be just a coordinate transformation, right? One can go to a different coordinate transformation and you'd see these quantities changes. So, when, for example, in cosmological perturbation that you mentioned, people work with something called Bardeen's variable. Those are gauge independent coordinate, coordinate independent quantities. That even if you change a different coordinate system, certain quantity will not change. So, what about question about your variable that you used?
See, I could not hear very clearly because there is disturbance, but I could get probably what you are worried about. That perturbations, these perturbations are for the relativistic stars with a fluid. Okay, I am not taking the, I didn't show the cosmological space-time here. So the thing is, the fluid, when it, say there's a motion in the fluid, these trajectories, so if you take co-moving coordinates, I showed you one of the cases, where still you will say the perturbation in the geometry was there, and in the other Schwarzschild coordinates, I have shown both the radial velocity as well as the matrix changing. And that is a standard thing, so I don't see that changing coordinates would change that.
No.
When we talk about perturbations, we are talking about a shift in the trajectory of the fluid.
No. If you do a perturbation in a general relativistic background, right, you will have a quantities that you are calling perturbation. I can generate those quantities by simply doing coordinate transformation. Okay, so you'll see this is a combination of matter perturbation as well as geometric perturbation together will form something called gauge invariant quantities. That is the standard computation done in cosmology. For your case, you are not doing that. So I'm saying what
that's
I'm
what
asking.
I'm doing. No, that's what I'm doing. See, I told you that H mu and xi are the two fundamental quantities. What am I doing is adding a source to the system. What is it that perturbs the system? Is that what the noise is the main point here? You know, and that I'm specifically saying that is it is only the matter fields giving rise to those noise. That's what I'm saying. These are induced perturbations, you know, due to these effects.
No, but you see, in Einstein's equation, you can take something from the left-hand side, add it to the right-hand side, right? For example, cosmology constant, you can add either to the left-hand side or also the right-hand side. So what you're adding to the right-hand side, I can equally absorb that in the metric perturbation, right? Just think about algebraic expression.
Probably whatever you're saying, I think it comes from what is your aim? You know, what do you want to do? Here, I want to show that the internal, fluctuations, and they are perturbing the system. So how you divide or how you place your GR system is this Einstein's equation depends on what you want to do. That's what I think.
So can you please go back, because I just like to see the difference, because it's the standard perturbation that are done in general relativity. Where does your formalism differ?
So for example, actually, so
maybe in the first slide you had an equation. Maybe you can go there. So what is the difference from the standard perturbation that was carried out in literature and among this?
So this tau AB is the added term, and it is defined on the background space-time. It is not defined on the perturbed space-time, is what I mentioned. This is new term. Everything, all these things are known. This is the new thing here. This is defined, as I said, and this is covariantly conserved.
No, but I mean, maybe I'm missing the point. I mean, so any perturbation will have a term, right, of that form. So what distinguishes this term from the other perturbation term?
This is as I mentioned, this is a fluctuation term which is defined stochastically. This is a stochastic term. Okay. So these are, so this is, if you, this particular thing, this is for the quantum fields, as I said. Quantum fluctuations. So we are adding first for the quantum fluctuations here on the background, in the background spacing for the semiclassical case. Okay. Yeah.
But we do the same thing, right? That's the standard perturbation theory. What I'm trying to understand, what is the difference thing that you're doing? Because the standard perturbation theory also do the similar kind of perturbation, right?
Standard perturbation theory doesn't involve tau AB. As I said, this is the new thing. Standard perturbation equation is without this tau AB. It only consists up to here, not this plus tau AB.
Are you sure about density perturbation in the cosmological theory, right? They write all the term matter perturbation as well as geometric perturbation.
So as I said, perturbations, I'm using two different terms, perturbations and fluctuations, even though both are stochastic. So the fluctuations I'm saying is like the Brownian particle when you add the stochastic source. So you define between, basically the geometry and the matter field from the statistics. So I am doing this kind of a division in the Einstein equation using the principles of statistical physics, where you divide the environment, bath, and the environment and the system, kind of a thing. So geometry is the system, and the matter fields are the environment, physically speaking. So that's what I said. It depends on what you want to do and how you divide the system is in your hands. What is your aim to study? What is the aim with which you are trying to study?
No,
So
the reason I'm asking, for example, right, CMB perturbation, right? So where people
no, you cannot, because this tau AB it is very different than tau ABG is a new term. This is the basic new term in the theory. So if you don't like, you already have the theory, whatever theories you have.
No, I'm just trying to understand. For example, let's say the case of say temperature.
So I would suggest you have a look into this Living Review article. So quite elaborately, they have discussed all these points quite elaborately, Bailo, Ku, and Verdaguer. So it is the same which I am doing for this. So all these questions which you are asking all, you will find all the answers here in this review article, Living Review article. It is in 2008.
No, it's okay. I mean, I'm just trying to understand what is this property of this term that separates this from this say other temperature fluctuation, right? And you're saying matter fluctuation.
Not necessarily temperature fluctuations, any fluctuations of the matter field, whichever matter fields you are taking of the team unit. So in the ordinary equations, you are asking me what is the new thing I'm doing. I'm saying the new thing is tau AB, which is basically fluctuations of the stress tensor, whatever stress tensor, the matter fields you take. And how you divide between your matter fields and geometry depends on what you want to do.
So I thought that's what we have been doing, right? I mean, you're saying that matter field fluctuation has been there in cosmological perturbation theory for ages, right? That's what the CMB perturbation theory matches, right? If you look at the CMB observation like WMAP and other things, they are doing exactly the temperature fluctuation measurement, right? So they are matching with the theory also. Now I'm just trying to actually understand what is the difference between the matter field perturbation that they are doing and what you are doing.
So this, I think, coming from the matter within themselves, CMB fluctuation is an external density and pressure fluctuation. So here it reflects in the Einstein's equation itself. So there you have to kind of have a perturbation. Here also perturbation is added, but all this coming from internal. There is no real pressure or density fluctuation, right?
So as I mentioned earlier, cosmology also they do work with perturbations and stochasticity, but that's different.
Maybe I don't see that. That's what I'm trying to say. No.
I have not shown cosmological perturbations here. What I have shown is specifically done for relativistic star dense matter fluid.
But even if it is applied for neutron star, for example, it is not going to be the density fluctuation of way standard it is done to find out the instability of a neutron star that involves the fluctuation or the perturbation in the density and the pressure, which results to various modes. These are internally coming from the different points, 2-point correlation function. That is, at different points there is a stochastic fluctuation whose mean is going to be 0, because these are built into the Einstein's equation or Einstein-Langevin equation.
Yeah, so maybe Rajesh, you can talk later. I mean, I'm just trying to see like how do we control this the tau AB externally? Like if there are other equations for
we do not control tau AB at all.
It has to come from the theory or what kind of you have put the kernel, right? That kernel decides the kind of a fluctuation it can give.
Okay, thanks. I mean, so
Yeah, let's start.